and is ready to give or share the matter and angular momentum at an early time. And when it does, they can be spun back without any change in the magnetic field. And based on you can accrete matter, and this is the line denoting the constraint coming from that. This dead pulsar might have lost the magnetic field strength. And then when it's brought back, it appears with lower magnetic field. And the good news is that it can now be spun up to a faster rate. If it happens to have a very low mass companion, and you see such examples in reality, which are called low mass X-ray binaries, where actually this action is occurring, where a dead radio pulsar is getting help from a low mass star which has evolved and now accreting matter onto the star and is brought back to life and is deposited or is spun up to a very fast rate, up to almost 1.5 millisecond, which is the limiting rate for the neutron star to survive. So what kind of history they will have, what kind of life they would have after they're dead, will be decided by A, if they have going to get some help, and when they are going to get the help. Based on that, their life history will be determined. But when they are born again, they, particularly when the help comes, when they have lost a lot of magnetic field, and by the time the low mass companion gives them help, they have learned their lesson. Earlier, they used to spend energy very quickly and lose their energy and lengthen their period. Now they have learned the lesson and they have become misers, wiser and misers. And now they lose energy at such a slow rate that they can live for as long as the Hubble time. And so they can live forever. So with vengeance. Of course, you can ask how often one can get such a help. It turns out that most pulsars are born in binaries. Whether they remain in binaries after the first explosion is a question that will be decided based on what happens during the explosion. But if the binary survives, then they have hope of getting some help eventually when they die as radio pulsar. I will not go into the details. This has been a well-studied field, and different paths will be taken in the life history based on the nature of the companion, the kind of survival occurring of the binary in the first explosion and in the second explosion, and so on. But when the millisecond pulsars were first discovered, that object was discovered as an isolated pulsar rotating at close to the limiting speed of rotation of pulsars, 600 times per second. It was Radhakrishnan and Srinivasan who, otherwise it has no business appearing the way it is appearing, with low magnetic field and such high spin. And so this was, of course, was verified with the further studies and large number of objects discovered since. And it's a well understood mechanism. Of course, the traditional binary pulsars were discovered in 1974 by Hulse and Taylor using the Arecibo telescope, which won them a Nobel Prize of 1993 because it was a relativistic binary, and they showed that the predictions of general relativity that Einstein had made were actually measurable and were exactly as quantitative even as predicted. So this is the famous figure which you might have seen often enough, and this was classic study that was enabled by binary pulsars. There is a new observatory now. After all, the binary pulsar of Pulse-Taylor provided a observatory or provided a laboratory that allowed us to study the effects of the gravity and the implications in the framework of GR. You could see only one of the objects as a pulsar. The other object, although being a neutron star, was not seen as a pulsar. Now you have a new laboratory made of two pulsars going around each other. And this has opened up possibility of conducting many more and more detailed GR tests. And this is a very active field of research. The millisecond pulsars, having learned not to lose energy very fast, slow down naturally very slowly at the rate of typically 10 to the minus 18 seconds per second. And so these naturally provide very stable clocks. They compare very well, or sometimes are better than the terrestrial atomic clocks. And people are hoping to use these, a set of objects, which are stable clocks located in different regions of the sky, regions of our galaxy, and whether studying their timing very accurately would provide a way of detecting gravitational waves. And this is another active area of research that you will come across. Many of you will be participating in this in years to come. Radio pulsars, I will not spend too much time on it. I think we have lost a lot of time due to these interruptions. We now know about 2,000 pulsars, so almost 3,000, close to 3,000 pulsars now, which is typically about fifth of the total number of pulsars are probably 20,000 pulsars that we will be able to see. We have seen about 1/10 of it. And pulsars have their own signature of radiation. The blip of light that we get, if we zoom into, we will see lots of details. And those details are very intriguing, even in the average sense. And they repeat this signature time after time, decade after decade. And we have observed them for almost 5 decades now, and the signatures remain the same. But that is only in the average sense. If you look at them individually, they differ so much that sometimes one wonders how come the average profile is the one like, for example, what is shown at the top, and individual pulses look nothing like the average pulse, nor like each other either. And this behavior can be systematic at times. Let me skip over this and say that, okay, I think I've skipped too abruptly. Let me go back. And these signatures that you have of average pulse are seen, they might look different, dramatically different at different energies. Sometimes, for example, in the gamma rays, you see an interpulse or an extra pulse here in the Vela pulsar, which is completely absent in the radio. So to study them, one has to study them at large number of energy ranges to completely understand these objects. We also see them in the radio at different frequencies, and we see the signatures systematically changing as a function of frequency. Here you can see the two components, the separation between them systematically changing, the pulse intensity, sub-pulse intensity also changing systematically. So what we believe is that, and so this is borne out very well by most of the observations. But what is important is to realize that pulsar radiation is has very high brightness temperature. It's very bright and could not be produced by any other known incoherent process. So it necessarily requires large number of radiators radiating in phase coherently, like in masers and lasers. But how to produce some large number like this? And this large charge density, which is required in the presence of magnetic field, is produced by first generation of large electric field because of the rotation of the magnet, which produces as high as 10 to the 12 volt potential difference. And this potential difference acts as an accelerator. You throw in any charge here, you will find charges will get accelerated to tera electron volt energies. And these charge particles at high energies will emit gamma rays, and gamma rays will, in the presence of magnetic field, will produce electron-positron pairs. And this is a beautiful example of how energy conversion to mass occurs. And the pairs produced, electron-positron pairs, themselves are energetic enough, and this process continues, and you get a cascade of pair production, and you get large amount of plasma produced along the magnetic cone. And this plasma, when it flows outward along the curved field lines, we get the radiation that we see. And given the large current densities, we get large number of particles in volumes comparable to wavelength cube, and they produce coherent radiation that we see. I will not go into the details of this. I can come back to it if there is any related question. But what we have at the heart of radio radiation production is a powerful dynamo which produces a high potential difference, basically produces large electric field, and that's where the acceleration occurs. Gamma rays are radiated, pairs are produced in the presence of magnetic field, and this avalanche of pair production leads to relativistic particle flow along the cone, which has curved magnetic field, and radio radiation is produced there, which comes out tangential to the local magnetic field as the charged particle travels along this curved lengths. Although all this can be stated, the key mechanism of the amplification and how all this really occurs in detail is unclear. We have been able to study the details, rich details, using several phenomena that one observes in these pulsars. We see systematic behaviors in these objects. When we look at the light from pulse to pulse, we see the pulse location changes systematically, the pulse sometimes disappears suddenly, and so on and so forth. And there are other changes as well. And there have been classic observations of one pulsar which has shown a part-time radiation where it radiates for a week or so and then doesn't work for several weeks. Pulsars are known to show nulls or stoppage of radiation at short time intervals, but this was an extreme example. And this allowed us to study how the which supports the picture that we painted, where the pair production and the high current density requirement was underlined. And remarkably, these measurements support within a decimal place the prediction made by Goldreich and Julian early on about the presence of magnetospheric charges and the currents that will be seen in the self-consistent way. You see the coherent radiation, that means large number of particles radiating together, and they have implications. You will find that you will get manifestations of this coherent radiation, because remember, this coherence is not just in time, it's also in space. Large volumes of charged particles are radiating together. And so in the transverse direction, you will also see manifestations of these in terms of diffraction patterns and so on and so forth. And there are examples which I will not go into. You will also see systematic behavior from pulse to pulse, which is called marching subpulses or drifting subpulses. And if this is occurring due to any, firstly, this shows that there is emission within the cone is patchy, and the patches are rotating about the magnetic axis. And people have proposed mechanisms for that happening. And you can invert this process. And although you sample only a tiny bit of this circle, a small chord, if the circle itself and the pattern itself is stable and moving about some axis, you will find that although you sample a single chord, at the different rotated version of the pattern, you will sample different part of the pattern. And by putting these together, you can construct the pattern that is responsible for the emission and the behavior of drifting subpulses that you see. And now you can begin to even monitor the weather on the pulsar. And this can be done, of course, you see it within a certain ring because inner part is not visible. But the effective resolution that you are viewing the pulsar emission here at is actually sub-pico arc second. This is the highest resolution that you can ever imagine in not just astronomy, in any field for that matter. This is like seeing a bacterium scale on Jupiter distance. Of course, as I said, you don't see the inner part, but if your chord is actually a diametric cut, then you will find that you can reconstruct the picture of the entire cone by using diametric information. And as the pattern rotates, you can construct the full picture of the pattern. Of course, you would like to study as what happens at different heights as these bunches radiate and come out streaming at relativistic speeds. But to be able to do that, we know fortunately that different frequency radiation comes at different heights. So to study this entire volume of the emission cone, we can take resort to studying them at different frequencies. But now we need to study them at various frequencies simultaneously. And that can be done, for which there was no available receiver on the instrument, and one could build such a receiver, which RRI did at the Green Bank telescope. Focus, this instrument was put, and multiple frequencies were observed simultaneously. And this is the first tomograph made. And this shows whether things happening at different frequencies, namely at different heights, because the correlation between the frequencies and heights exists. We can now study them, how these bunches. Now, going back to this, earlier I had mentioned some examples of the nebulae that they produce. Pulsars are zipping through the space, and they can produce, as I said, wake-like structures in the direction or along the direction of their motion, with a bow shock-like feature at the tip of this nebula that they will produce. But they can also produce a wind nebula by the wind that comes out, which we just saw. that it carries as much energy as the energy loss due to the dipole radiation. A spectacular nebula produced by the Vela pulsar was observed with remarkable clarity with the Chandra telescope in X-rays. And this is the famous picture of it. What is shown here is a beautiful X-ray nebula with arc-like structures and a jet-like structure delineated very clearly in the middle of it. And the pulsar location is also seen as a bright spot here. And this pulsar nebula can be explained as a combination of a flow of charged particles that we just invoked to understand the radio radiation. So imagine a hose of paint which is being rotated, and the paint is sprayed on a cavity which the pulsar itself has made. What will you see? You will see two circles corresponding to the two poles or two-ended hose. These circles seen in an arbitrary orientation will be seen as ellipses. And if the light coming towards you is going to be brighter, you will see them as bright arcs, which are pieces of the elliptical track. And this is exactly what is seen in this. If you do the fits, it fits in with the geometry of the orientation associated with the magnetic axis and the rotation axis of the star. You can ask what happens to this charge flow as it comes out after producing the radio radiation. When the rotation is no longer sustainable with the star, you will find it will produce a toroidal pattern of flow of charged particles as they move towards the cavity wall. And as they do so, they will find that what was a dipolar field earlier has been turned into a toroidal field about the the rotation axis of the star. And there is a charge flow outward, which is largely perpendicular to the rotation axis. And there is magnetic field, which is wound around the spin axis, which is also perpendicular to the rotation axis, but also perpendicular to the direction of the flow of the charges. And you will find that this will lead to a force acting on the charges, which will deviate them only in the direction which is containing the plane of the rotation axis. It will only spread them latitudinally. And you will find now the pulsar has not only a pencil beam of charges, but it will also have a fan beam, a spread beam in one direction. And imagine paint being thrown. It's basically painting with a narrow brush as well as a broad brush. And when that is done, you will see with the broad brush, you will see the fuzzy emission, which you see in this nebula, and the orientation of this kidney bean-like structure will be decided by how the rotation axis is oriented with respect to us and the magnetic field is oriented. And when put together, the effect of both these, you will see a model of the spectacular nebula. This is the simulated version. And so the simple geometric picture can explain beautifully designed nebulous structures that pulsars produce around themselves. What is nice about it is they are painting their rotational history on the wall of the sky. An example of that can be seen here, where there was a famous observation reported, and it was called cosmic fire hose. And this was zooming onto this Vela pulsar nebula that you saw, but on the jet-like feature that one had seen, And one observed through pictures taken at a few epochs that this jet-like feature was dangling around. It was not stable. And this attracted our attention, and we free precession of the star. What one is looking at, we believe, is like the top precesses around its rotation axis, instantaneous rotation axis itself precesses around some mean axis. Here we are seeing free precession of the star, and that is what is showing the variability. This could be simulated, and we can, I think this thing is not working. I think that's because we re-began the, okay. Later on, these observations were repeated, and unlike in some Hollywood movies, the sequels are of the famous movies are never as good as the original. Here, the sequel of this movie made by NASA's Chandra X-ray Observatory is actually better than the first one. And you can see the dangling has been now clearly observed, and the signature of free precession is loud and clear. And this is a beautiful example of free precession of radio pulsars. And as you will find, what it is doing and what is showing is showing its rotation history painted on the wall of the sky. So what is seen here as an orientation of the jet is what was the orientation whatever many light months ago or many light years ago. And what is seen closer to the star is what is its orientation presently, and so on and so forth. Importantly, as you might recall, I had made a comment about radio radiation not showing an interpulse. Here, the radio radiation, although not visible, the presence and the imprint of the double-ended hose is clearly seen. One can also look at another picture that was shown in the talk this morning about the crab pulsar, which also shows a beautiful X-radiation nebula, and this is what is seen. And if you, this is the picture just in X-rays, showing the arcs and jet, which is also twisted jet here. And if you do simple simulation, incorporating different aspects one by one, you will see that the twist as well as the overall nebula structure can be reproduced by invoking free precession and a simple geometric picture of the hose carrying the two-ended hose of charged particles depositing their energy on the cavity wall and producing a glow of light that we see in X radiation. So I call these writings on the wall, and this is a very strong evidence for collimated particle beams from pulsars. Also, we have found the evidence for pre-precession of stars, of pulsars. And these might be, people can calculate how much gravitational radiation might result from such a thing. So pulsar mysteries will continue to unfold and be heard, and many of you are going to be actors in this drama of revealing the pulsar mysteries. And as I said, there are almost 10 times more objects to be discovered. We have two holy grails already, one holy grail already discovered, which is the pulsar binary or double pulsar binary. We have yet to discover a sub-millisecond pulsar and, of course, a black hole pulsar binary. And I wish you all the best, and I hope some of you will feel attracted enough to go and participate in this field and create waves in your own ways. Thank you for listening. Thank you. I'll be happy to answer any questions you might have if you're still connected. Let me see where to get the chat box. Yes. Okay. Right. All right. I will go from the top. Okay. I think the first question, if I get it right, is how does a neutron star die? From Rashmi. And I think a probably related question is, do pulsars die other than dying through collision with black holes? And why do white dwarfs then convert into black dwarfs? Okay, let me go first to the neutron stars themselves. Yeah, the neutron stars will live forever unless being disturbed by anyone. But if they happen to be in binary, and if they happen to be in binary where their the end history is, if they happen to have a star which is still evolving, lots of things will happen like the way we described. But if the second star also happens to be a compact star, degenerate star, then the only way they are interacting is not through any tidal interaction, but largely through gravitational interaction. And as they spin, as they orbit around each other, they will lose energy and through gravitational radiation, and then they will eventually, the system will coalesce to form a new object, right? And give out huge amount of energy in form of gravitational waves as it spirals down. Now, that's how they can die. Unless they are somebody to interact with, they will not evolve into anything. They might accrete matter from just surrounding, but that will be at a very slow rate, and that they're not going to do anything in interesting times. Okay. Coming to the next question, did I answer that question? Rashmi? Okay. Now, second question is, I think, do pulsars die other than dying due to collision with black holes? See, for things to collide with somebody, they have to be together in by some initial arrangement. Their sizes are so small and there is so much space that they are unlikely to run into each other by just chance. So if they have already somebody with them by the intrinsic nature of the system from the way it was born, then interesting things can happen. So they're unlikely to. So the pulsars as radio pulsars, of course, they will die because their radio radiation stops and we don't see them any longer as radio pulsars. They might radiate as they do, even in the graveyard. They can radiate X-rays and the pulsation is seen during the action where they are accreting matter from their companion star. So they are X-ray pulsars, and X-ray pulsars will last for certain phase during the accretion. And once the accretion is over, that if they have been brought back to life as radio pulsars, they might act as radio pulsars. They might produce X-rays due to other reasons relating to the magnetic field and their rotation as rotation powered pulsars, quite independent. Okay, coming to the next question, why do white dwarfs then convert into black dwarfs? Dwarfs are. If you can educate me, I will try to answer that question. Okay, the next question is, a few days back, origin of fast radio burst was detected, assumed to be coming from magnetars. Yes, I think this might be the real story. Magnetars could be the sources of fast radio burst, which is always suspected. They are, even if it's not entirely true, they are certainly very strong candidates for it. And do we have any concrete answers behind the science of emission? Well, we have some answers, but more questions. We still do not know how the plasma processes conspire to produce such huge amplification. And the important thing about the amplification is, you might say, okay, we know if, large amplification is produced, you should be grateful for the maser or the coherent action. Yes, but this is a very large gain, which depends on, very crucially, on the number of charges radiating. How come pulsars keep their intensities so steady, even within the range that they might vary? The overall range is pretty steady. And so that stability, given the nonlinearity as implicit in the amplification process, is still a puzzle. There are some pulsars which give out very steady intensities. I showed you some examples of where the intensity varies very crazily from pulse to pulse. But there are very steady emitters where every pulse looks like every other pulse. And in them, one wonders what regulates this amplification factor. And so those are unsolved questions. But yes, we generally understand their overall mechanism. We have an overall picture that provides us a mechanism to ask further questions. Okay, the next question is, how do neutrons in pulsar cause magnetic field, as we know that neutrons do not have a charge? Yeah, so when we call them neutron stars, they are not made of neutrons all the way to 100%. Okay, there are ions and electrons and protons inside, enough to circulate and sustain the penetrated magnetic field. Okay, so they of course need to be large in number, but in fraction of the number of particles, they are tiny. So when we say a neutron star, we say predominantly made of neutrons. Okay. I don't know whether that answers the question correctly or completely. Okay, going to the next question. Can you please explain what a tomograph means in detail? Okay, so tomograph is essentially here, the context in which it is used is, we have a volume, we have a 3D object, and we are trying to study it in 3D by studying or compiling cuts of two-dimensional cuts or two-dimensional surfaces are studied, and doing that at every systematic step. Okay, why white dwarf is unstable? Okay, white dwarfs are not unstable. It's one of the stable configurations that a star, the compact star, can attain, where the degeneracy pressure of the electrons is adequate to hold the gravitational push inward. And so it's actually a stable configuration. But if the mass becomes larger than the Chandrasekhar limit, then you will find the gravity is stronger, and then the degeneracy pressure of electron is not enough to hold the inward collapse. You have to appeal to something else. And what is that? As in the neutron stars, you will find the neutron degeneracy pressure is adequate to hold further collapse, and that's how the next stable configuration is achieved in form of neutron stars. Okay, going to the next question. While detecting new pulsars in radio, do we come across any noise, and on which parameters do we separate pulsars, RFI, and noise? Yeah. Okay, so while we detect pulsars, firstly, the noise, the signal that we believe we receive from radio sky itself is a noisy signal. Okay, what we are trying to look at is the variance of that noise, which is proportional to the intensity. And by nature, all our estimation of even the intensity is uncertain by an amount by which the intensity itself is jumping up and down. So by nature, the radiation that we receive from the sky is completely noisy. It's pure Gaussian random noise. Okay, and what we are trying to learn about is what intensity it represents, which is given by the variance of this noise. Now that variance of noise varies in a systematic fashion in the case of pulsars, in a periodic fashion. And we detect or search for pulsars by their strong periodicity, okay, stable periodicity. The second signature we detect them by is thanks to their travel of these signals through the interstellar space, which happens to be dispersive medium, which means the radiation at different frequencies does not travel at the same speed, which causes the pulse to arrive, although it's radiated at the same time at all frequencies at the location of the pulsar, it arrives at our location at different times. And this difference in time or delay compared to one frequency of the other frequency radiation is well understood, and the delay progressively increases towards lower frequencies. And this leads to what is called the dispersion of the pulse when we see it. This dispersed pulse is a very powerful discriminator against typical radio frequency interference that might confuse us on the Earth. And so most of the man-made signals would look very different from the dispersed periodic signature of pulsars. And on which parameters we separate pulsars. Yeah. So I think those are the two things. So even if we had, many times we might have a peculiar situation where in our field of view, there might be more than one pulsar. How do we separate one from the other? They can beautifully be separated by this, the periods, the periodicities will be different, which means their spin frequencies are different, and their dispersion characteristics will be different. Dispersion, amount of dispersion will depend on the number of electrons encountered during the passage through the interstellar medium and through the ionosphere and all that. And that might differ in different directions. Also, it will naturally depend on the distance of the pulsar. And so even if we have many pulsars in one location that you cannot differentiate using our telescopes, that means we do not have resolution to separate them out, we will be able to separate them out based on their periodicities and dispersion characteristics. In fact, let me take you to, if are there any further questions? Okay, then let me take them to the next slide, which is, as much as it's related to the question that was asked. Now, this is not the sound that is produced by the pulsar, but we can produce that sound by playing or sending the electrical signal representing the pulsar intensity changes to a speaker and hear them like sound. And this is what we heard of a quarter second pulsar. This is how it will sound if the pulsar is to be like the Vela pulsar, 11 times a second. Or sorry, this is 4 times a second. This is 11 times a second. This is 30 times a second. And this is what I'm going to play now is 600 times a second. And for musically oriented people, that was the note E. And when a large number of pulsars are there, and if twinkling is producing changes in their intensity on top of what their original tone itself is, this is how they would sound. And I will leave you with this final audio, which is of 30 pulsars in a globular cluster. Some of them are fading, and some of them are coming loud at different times. This is how the orchestra will sound. Thank you.
Thank you, sir. Thank you so much for that lecture. That was truly wonderful. And the members of Astro Club and all our viewers, we really thank you for taking out your time to deliver this lecture for us. And to all our viewers, please stay tuned because, again, we do have more lectures for you in store in this Astronomy Week. And please stay safe and keep watching. Thank you.